To a professional IT technician, hearing an end user simply say, "the internet is down," is functionally meaningless. End users experience network connectivity as a single, seamless utility. But to accurately diagnose a failure, technicians must view that connection as a precise, multi-stage architecture. Look at this network demarcation line. On the left is the private local area network, or LAN. On the right is the public Internet Service Provider cloud. For data to cross that boundary, it has to be structured and routed. That structure is defined by the TCP IP model. This four-tier framework governs exactly how electrical signals on physical hardware translate into logical addresses, reliable transport streams, and specific software application services. Every piece of network communication relies on a dual addressing coordinate system, an IP address to locate the specific machine, and an application port to locate the specific software. To see exactly how these coordinates operate in practice, we are going to construct this network stack from the physical ground up. Mapping the data flow across these distinct layers allows us to transform a generic outage into a series of isolated, solvable technical variables. This diagram shows the complete hardware layout, starting at the foundation of our stack, the network access layer. At this layer, the system's sole job is to place data frames onto localized physical media, like copper Ethernet cables or Wi-Fi radio waves. Inside the local network, multiple hardware devices connect to a central switch. The switch forwards traffic strictly between these local endpoints. For wireless physical connectivity, an access point broadcasts the local network to mobile clients. To leave that local environment, traffic is sent to the router. The router's function is to divide a single physical network into logical subnets and direct packets toward the outside internet. That the router cannot speak directly to the ISP, it requires a modem to convert the local digital data into a signal the provider's physical infrastructure can read. The type of modem deployed depends entirely on the ISP's physical transmission medium. Cable internet utilizes the same coaxial lines built for television, making it fast and widely available in residential environments. DSL runs over standard copper telephone lines. Because of this older infrastructure, its speed degrades the further the modem is located from the ISP's facility. Fiber optic networks pulse light through glass strands, offering extremely high speed and low latency, though physical rollout is limited by trenching and installation costs. Where physical cables are impractical, wireless links like 4G or 5G cellular provide mobile access, while satellite connections offer global coverage at the cost of significantly higher latency. If this network access layer is severed, if a cable is cut or a modem burns out, no logical addressing or routing higher in the stack can occur. You always verify the physical link first. Assuming the physical hardware is operational, we move up to the internet layer. To route data globally, devices require unique logical identifiers. This chart outlines the primary routing coordinate, the IP address. The original standard, IPv4, relies on 32-bit addressing. It provides roughly 4.3 billion unique addresses, a numerical limit that modern networks have largely exhausted. Its successor, IPv6, uses a 128-bit architecture. This provides trillions of addresses, permanently solving exhaustion while offering native scalability and built-in security features. But a machine doesn't automatically know its own IP address when you boot it up. It has to acquire one. That automatic assignment is handled by the Dynamic Host Configuration Protocol, or DHCP. This graphic details how a device secures its network settings. It uses a four-step sequence known as DORA. First, the client broadcasts a discover message to locate a DHCP server. The server replies with an offer of an IP lease. The client sends a request to use that specific IP, and the server finalizes the transaction with an acknowledge packet. If this DHCP negotiation fails, Windows operating systems fall back to an automatic private IP addressing protocol, known as a PIPA. An PIPA address always assigns itself within the 169.254 range. It allows the device to communicate with other AP/IPA devices on the exact same local switch, but it completely cuts off access to the broader internet. Even with a valid IP, humans don't navigate the web using numerical coordinates. The Domain Name System, or DNS, translates a human-friendly URL, like google.com, into the correct routing IP address. Without a successful DORA process to assign an IP, or a DNS server to resolve domains, the physical hardware will appear perfectly functional, while the machine remains logically isolated. Once the IP address is secured, the system has to dictate the exact rules for delivering the data. This calculation occurs at the transport layer. This diagram compares the two foundational transport protocols, TCP and UDP. The Transmission Control Protocol, or TCP, is connection-oriented. It establishes a formal two-way handshake between devices before a single byte of data is sent. It enforces strict reliability. TCP utilizes error-checking mechanisms and requires the receiving device to acknowledge every packet. If a packet goes missing, TCP demands a retransmission to ensure the data arrives accurately and in the correct order. This exactness makes TCP the mandatory standard for loading web pages via HTTP, downloading files over FTP, and sending emails. On the other side is the User Datagram Protocol, or UDP. It is connectionless and operates on a best effort delivery model. UDP strips out the error checking and the acknowledgements. It simply fires packets at the destination. It does not guarantee delivery, and it does not guarantee the order of arrival, which drastically reduces processing overhead. This sheer speed is required for live voice calls over VoIP, video streaming, and rapid DNS lookups, scenarios where waiting for a dropped packet to resend would ruin the real-time experience. TCP prioritizes perfect accuracy. UDP prioritizes maximum speed. Forcing an application to use the wrong transport protocol results in either crippling latency or severely corrupted data. The data packet has now reached the correct IP address using the correct transport rules, but a single server might run a web page, an email client, and a remote desktop session simultaneously. The machine needs to know which specific software should receive the incoming packet. This table lists the solution: application ports. The port is the final logical coordinate, directing traffic to a specific software service within the application layer. Standard unencrypted web browsing is mapped to HTTP on port 80, while encrypted traffic routes through HTTPS on port 443. File transfers default to FTP on ports 20 and 21, or the secure variant, SFTP, on port 22. Email routing relies on a trifecta of ports: SMTP on 25 for sending, and POP3 on 110 or IMAP on 143 and 993 for retrieving messages. Network administrators frequently use RDP on port 3389 to remotely access desktops, and SNMP on ports 161 and 162 to monitor device health. Security appliances like firewalls operate heavily at this layer. They scrutinize incoming traffic and actively block or allow packets based explicitly on these port numbers. The IP address gets the data to the correct building. The port gets the data to the correct room. These 4 layers function as a single, integrated logical chain, linking every physical signal to its specific software destination. When an application generates data, it assigns a specific port number at the application layer. The system then applies the transport rules, either TCP or UDP, determining how strictly the data must be delivered. Next, it drops to the Internet layer, where the destination IP address is stamped onto the packet. Finally, at the network access layer, that logical data is converted into physical, electrical, or optical signals, routed through the modem, and pushed out across the ISP infrastructure. When connectivity fails in the field, attempting to guess the solution wastes time and resources. Professional troubleshooting relies on this exact framework. You move systematically, either bottom-up, starting with the physical cables and modem signals, or top-down, verifying firewall ports and application settings. By mastering this architecture, you stop dealing with ambiguous hardware errors. Every network failure becomes a traceable sequence of logic, waiting with exact coordinates to be identified and resolved.